My name is Shahab D. Mohageg. I'm the director of West Virginia University Laboratory for Engineering Application of Data Science. In this lecture, I will be covering collective fuzzy pattern recognition. It's part of the descriptive analytics that uses supervised fuzzy clustering. In this particular lecture, I will be talking about actual data from a shale asset in northeastern United States. I will show you the actual data for about 355 wells in order to explain how complex the data from shale assets are, and then try to answer the question whether there are patterns in the data. When you look at the data, how complex it is, you will clearly see that there is no correlation or pattern in the data that have been collected from field measurements. And the question is it possible to discover some hidden patterns in this data that could help us use that in order to build a model and optimize completion and production in the for shale assets. So with this, let me get started by moving toward this very particular asset. It's a shale asset in northeastern US. It includes large number of wells. We're using about 355 of these wells. The wells are completed and are producing from two formations, a shale formation on top and a carbonate formation on the bottom. You will find out that in most of the cases in shale asset, that is the case. You have multiple formations, and there are places that you have shale on the top and the bottom, and sometimes carbonate in the middle, or in any other combination. But you always see more than one formation to deal with. Here you can see the location of the 355 wells that we will be dealing with in the northeastern United States. This plot shows you the bubble point of 180 days cumulative oil production from these 355 wells based on their location. The size of the bubble shows how much oil they have been producing. Here the size of the bubble shows you how much gas has been produced from these wells, and finally here it shows how much water is being produced. And we are using this 180-day cum production as productivity index that we try to find out if there is any correlation between different field measurement and this particular productivity index. So in the next few plots, I will be showing you field measurement versus productivity index. The productivity index, again, that I will be working with in this particular analysis is 180-day cum gas production. You can use any other productivity index, whether it's gas or oil or a combination of both. Here we are concentrating only on gas production because mainly in this particular asset, gas production is the major production in northeastern United States. So in all of the plots that you see, the y-axis is the productivity index, and the x-axis are different field measurements from different categories that we will be looking at. And the idea is to look at the data and see if you can identify any patterns or trend in this data. In this plot, in this slide, you can see inclination and azimuth versus productivity index. As you can see, there is no pattern or trend in this data. Here you see pad drilled order, whether it's the first in the pad, second in the pad, third, fourth, or fifth, or sixth well in the pad that we have in 355 that we're dealing with. On the right hand side, you see the spot date. Here you see true vertical depth on the right and measured depth on the left. Here you see different characteristics of the shale formation, the formation on the top versus productivity index. You see porosity and the neutron porosity. You see TOC and net thickness. Here you see water saturation and Young's modulus. And here you see Poisson's ratio and minimum horizontal stress. And you can clearly see there is no pattern or trend in this data when you plot them against the productivity index. Furthermore, we have V Clay for the shale. And as you saw on the bottom, there is a carbonate formation. On the right, you see the plot of the V clay of the carbonate versus the productivity index. Here you see the sand volume and the carbon volume percentage versus the productivity index. And here you see TOC and gamma ray. The next item is resistivity of the carbonate and the temperature of the carbonate and how they correlate, if there is any correlation between them and the productivity index. Now you look at maturity and VP1. Up to now, we were looking at the field measurements that had to do with formation characteristics. Now we are going, the next two slides, you're going to see 4 different parameters that has to do with the design of the completion. Here you're looking at stimulated lateral length and shot density in shot per foot versus productivity index. And here you see the number of the stages and the total amount of perforations, total number of perforations versus productivity index. Now let's look at some of the implementation of hydraulic fracturing, the data from the implementation of hydraulic fracturing. You are looking at minimum injection pressure and minimum injection rate versus productivity index. Here you see the average injection rate, the average injection pressure, and here you see maximum injection rate and injection pressure. Here we're looking at the proppant per stage in pounds and clean volume of fluid, actually water, slick water in barrels per stage versus productivity index. Now we're looking at things such as ISIP, breakdown pressure. Here we're looking at pre-treatment SIP and post-treatment SIP and average gradient, average frac gradient. And finally, we are looking at operational conditions such as average tubing pressure for that 180 days and average casing pressure. And finally, the choke setting for these 355 wells. And so looking at the data, it becomes clear that there are no obvious or easy to find patterns in the data that has been collected from this shale asset. There seemed to be no correlation between hydrocarbon production or productivity index of the hydrocarbon that we showed from these hundreds of shale wells and all the field measurements that have been made, including, as you saw, the categories were formation characteristics, we had completion, design, and implementation, and finally, operational condition. Now, in order to put it in a bit more perspective, I'm going to put them all together in one slide. All the plots that you see here in this slide has to do with the shale formation, from porosity to neutral porosity to TOC to thickness to Poisson's ratio and so forth. And you can see that there is no pattern that you can see in this data, no trend in this data. This is the collection of the plots that I showed you earlier, but we're putting it together for carbon formation. The series of plot that has to do with completion design, the series of plot that has to do with fracture implementation, and the series of plots that has to do with rock fracture characteristics. And finally, the 3 plots that has to do with operational conditions. And you can see that there is this is very much true with all the shale assets throughout the world. This has to do with the complexity of the hydrocarbon storage and transport in unconventional reservoirs. And this clearly shows you that using traditional and conventional techniques such as decline curve analysis, rate transient analysis, numerical reservoir simulation, in order to model fluid flow and production from shale wells is overwhelmed by gross assumption and simplification. In other words, it clearly shows as we move forward for the entire course, of course, but by now probably all the reservoir completion and production engineers have come to this conclusion that conventional techniques of modeling the physics does not work in unconventional reservoirs, specifically speaking for shale assets. So that is why shale analytics, which is the application of artificial intelligence and machine learning, can change the whole thing and provide you with a lot more realistic model and analysis of the data that is actually measured and collected from the shale fields, rather than just soft data that people are guessing and assuming. Thank you very much.